Good morning, everyone. Welcome to this second SEMNI day. Thank you for being with us in this very special day, just before the Good morning, everyone. Welcome to this second SEMNI day. Thank you for being with us in this very special. Okay, we have some delay. My apologies for this echo. Okay, we have with us Professor Matteo Giacomini and Marino Arroyo, who is the Secretary General of SEMNI. Professor Matteo Giacomini is Associate Professor of Computational Engineering at the Universitat Politècnica de Catalunya in Barcelona, affiliated researcher at the SEMNI, the International Center for Numerical Methods in Engineering, and also affiliated faculty at IM Tech, the Institute of Mathematics of UPC Barcelona Tech. Dr. Giacomini received a bachelor and master's degree in mathematical engineering from Politecnico di Milano, and the PhD degree in applied mathematics from École Polytechnique, Université Paris-Saclay. Dr. Giacomini's research activities lie in the field of computational science and engineering, encompassing the development of advanced discretization strategies for the approximation of partial differential equations, reduced order methods, scientific machine learning, and shape and topology optimization. He is fellow of the Serra Hunter program of the Government of Catalonia and recipient of the Juan Carlos Simó Award by SEMNI in 2022. And this is the ultimate reason why, because he has been invited to be here today with us, giving this talk, which is entitled Enhancing Adjoint-based Topology Optimization from Mesh Adaptation to Machine Learning. So, Matteo, thank you very much for accepting our invitation to give this lecture, which has a very, very nice and interesting title. So, the virtual floor is yours.
Thank you, Elias. And first of all, let me thank also the SEMNI Imaging Board for this invitation. I'm really glad to be here. Would have been nice to see you all in 3D, but this is what this powerful means allows us to do today. So today I'm going to talk about, as Elias mentioned, about topology optimization techniques, and specifically how we can do to enhance them using mesh adaptation and machine learning. And I want to start by acknowledging my senior collaborators, Marco Discalciati from Loughborough University in the UK, Antonio Huerta from UPC SEMNI here in Barcelona, and Simona Perotto from Politecnico di Milano in Italy. And of course, the students that allow me to present these results today. So Daniela Raya is a former PhD student from UPC. Enrico Savone and Giorgio Zamberlan are current master students from UPC. Ben Evans is a PhD student that I'm co-supervising with Marco Discalciati, and Guillaume Barroso is a former postdoc that I worked with him and Antonio Huerta. So let me briefly start with where this work starts from, which is indeed topology optimization for structural optimization. And I will be mainly talking about structural optimization in this topic, but I will try to sketch a bit also the idea that are behind the motivation of this work, which has a bit of a broader scope. So here to the right, we see basically a cartoon of how a high-fidelity optimizer works. There are basically different steps. These are technical details that I will go through later on. Basically, there's a first step in which we try to optimize a certain criterion. For example, in this case is minimizing the compliance, applying a vertical load in this portion of the domain. But usually these algorithms tend to provide structure which are optimal from the mathematical perspective, but they're not really manufacturable, so there are some issues. And to work around this issue, other iterative algorithms, generally speaking, called filtering or penalization steps, needs to be performed, and they also have a certain cost which is not negligible. So basically, for each setup that we might be interested in, for example, in this case, linear elasticity, but we might think about coupled problem, fluid structure, fluid thermal, and so on and so forth. So for each physical model, each boundary condition setup, and each set of material properties, basically we need to run an iterative algorithm in order to determine the optimum. And by optimum, I mean the optimal topology. I will go back to some details in a moment. The optimal shape, the optimal solution, so the optimal physical variables, displacement, stresses, velocity, and so on and so forth. So this, of course, has a high computational cost because at each iteration, we need to solve to approximate a set of PDEs. These PDEs are what we call the state equations. So the equation that model the underlying physics. It could be linear elasticity, Navier-Stokes, thermal problem, but also some extra equation, which are called adjoint equation, that allows us to compute sensitivities, how variation of our design variable influences the value of the function that we try to optimize. And of course, we also need to update the design. So as you can imagine from this brief summary, these techniques are pretty complex. They require to give accurate and robust results. They require some work, but also they are extremely expensive. Why so? Because at each iteration we need to solve our favorite method. We are going to use finite element, but you could use finite differences, spectral elements, or whatever approximation you prefer. But we need to solve multiple times, multiple instances of a differential equation, which could be nonlinear, which could be multi-scale, and so on and so forth. So it's then critical to rely on surrogate models to make this computation affordable. So as I mentioned earlier, I will be mainly focusing for the sake of the methodology on structural optimization, but let me first take a brief step back and try to provide a bigger picture of why we're interested in these problems. And basically, this boils down to one of the objectives of the European Commission at the moment towards 2030 and more long-term 2050, which is the goal of devising a sustainable and resilient EU. So we'll try to briefly sketch what we are interested in when we talk about sustainability and resiliency. And of course, I'm sure you've heard talk about the European Green Deal. So the objective of the European Commission to make Europe the first climate neutral net zero continent on Earth, and the role, of course, that electromobility plays in this context to reduce carbon emission. And indeed, within the European Green Deal, the European Commission has set very ambitious objectives of reducing carbon emission by cars of 55% by 2030. So sustainability means reducing our carbon footprint, and the mobility plays a key role. But at the same time, we are also facing the consequences of global climate change by observing more and more extreme events that affect our lives. And so I'm sure you're all aware, if you're living in Catalonia, we've barely seen any drop of rain in this year. So extreme events like droughts, heat waves, but also flooding, hurricanes are becoming more and more present in our lives. And the recent press release by the European Commission identified as critical for the EU to put in place some mechanisms for protection and for facing these effects of climate change. And this is what I refer when I talk about resiliency. So with this in mind, sustainability and resiliency, I want to present the two engineering problems that drive our research at the moment. So try to answer what computational engineering can do in the context of a resilient EU and a sustainable EU. So the first one related to sustainability, as I mentioned, is battery electric vehicles. This is associated with the Sustainable Development Goal number 11 of sustainable cities and communities. And the idea is to make battery electric vehicle employable by the majority of the population. We need to make them efficient, first of all. So the idea is how can we optimize the battery thermal management of battery vehicle to extend the lifetime of battery and to extend their range of applicability in order to guarantee that they're usable in a daily life. And of course, this problem is complex because it entails optimization, specifically shape optimization and topology optimization. It requires high fidelity models to represent the underlying physics, which is a coupled thermal flow with the problem. But it also, but these are also problems which are expensive from the computational viewpoint. So they're multi-physics, they're coupled, and require appropriate surrogate models to be computed in reasonable time to allow industrial design. And of course, coupling high fidelity and surrogate models, the following step is indeed to determine multi-fidelity models that are able not only to use simulation, but possibly also data that come from sources with different levels of reliability, and use all this information to determine the optimal shapes and optimal topology. And this is what we've started working with in the master thesis of Enrico Savona. Here you can see an optimized topology for a heat sink channel, the resulting temperature distribution. Here the objective is for the temperature in the solid part, so in the black part, to be as uniform as possible. And here the corresponding velocity module. The other problem that I mentioned earlier related to extreme events has in mind the Sustainable Development Goal number 6 about clean water and sanitation. So in presence of extreme events like floods, hurricanes, the critical infrastructure that we use in our daily life, like pipeline or sewage system, can be critically affected. And so in those cases, how can we provide easable, deployable manners to have access to clean and safe water? And to do this, what we can deploy are filtration systems or microfiltration system. The key aspect of this system is that they need to be easily transportable. They need to be efficient in terms of energy consumption. And so they have a lot of restriction that make these devices not something that can be simply set down in a certain place, but needs to be able to, we need to be able to move them easily. So it's critical in this context to devise digital twins of these membrane filtration systems to perform optimization, again, shape optimization and topology optimization, but also control in real time of these devices. And the challenges in this context are the fact that the underlying physics is represented by coupled system, Navier-Stokes, porous media, and so on and so forth. And those we need effective domain decomposition techniques that are also able to treat not only the high fidelity simulation, but also the local surrogate models that are constructed in each subdomain. And this is what we started looking into with the group in Loughborough recently. So these are the two main motivations of all the work that I'm going to present today. But for the sake of simplicity, I will try to stick to a bit more abstract framework and talk about structure optimization henceforth. So what is topology optimization in a nutshell? Here you see the abstract mathematical formulation of the method. The idea is that we want to determine the layout of the domain. So the layout, we mean the material distribution that we have in this big box. This material distribution has the goal, need to meet a certain criterion. So we want to minimize certain cost functional represented in blue over here. And this cost functional, of course, depends on the shape of the domain, but it can also depend on some physical variables. So, for example, this U. And this physical variable U, generally speaking, is the solution of a certain PD. In this context, we are going to consider the linear elasticity equation. So this will be the standard linear elastic problem. But this is not all. We also need to introduce additional constraints, which are geometric constraints. Okay. This is the report here to the right is the compliance minimization of a bridge in which we are applying a vertical load in this position. Okay, so what are the computational challenges in this context? Well, as I mentioned earlier, this objective functional depends upon the solution of a PD. So we need to solve multiple times a PD using finite elements. Okay. Moreover, these problems are generally imposed in the sense that there exists no unique minimizer to this problem. There are multiple minimizers for which we need to introduce actually geometric constraints, which could be constraints over the volume, constraints over the perimeter. And moreover, this problem tend to converge to solutions which are physically not admissible in the sense that if you look at the structure, we can interpret the white region as void, the black region as solid material. But what about gray? Well, gray is what is called an intermediate density, which is not something that is manufacturable. So this problem also require penalization techniques, which are sometimes also called filters in the literature, what often called filters in the literature, in order to get to physically suitable, physically admissible solutions. Okay, so to put a bit more of an engineering perspective to it, let me specify this J, G, and calligraphic L for the case of linear elasticity. So we have that the calligraphic L is the linear elasticity equation, where sigma is the Cauchy stress tensor, U is the displacement field. We use the standard Hooke's law to model the relation between displacement and stress tensor. The objective function is the minimization of the compliance, or the work done by the external forces. In this case, there is only a surface force applied, which is called G on the Neumann boundary, and the geometric constraint is a maximum volume constraint. So the volume of our structure, represented by this integral, needs to be bounded by a certain user-determined threshold V star. And most importantly, contrary to what is standard in optimization, what we are seeking is not really a function, but the design variable is represented by an expression, a suitable form, a suitable topology of our domain that needs to be selected in a set of admissible shapes, or in this case, admissible topologies. Okay. So in the literature, there have been many ways of approximating this problem. And what I want to start with is, briefly reviewing the homogenization method. So the idea of homogenization goes back to the work of Benzo and Kikuchi, and was later formalized mathematically by Creux-Araler. And the idea of topology optimization by homogenization is to define a composite material. This composite material is characterized by two variables, a material density theta, and what is called a homogenized tensor C star. Okay, so we can rewrite our problem, our original compliance minimization problems, using the homogenization method by employing these two variables, the material density and the homogenized tensor. So what is critical is to rewrite all the functional and all the variables that are appearing in this problem in terms of theta and C star. Of course, in terms of the constraint over the domain, it's straightforward to see that basically it boils down to rewriting the integral only accounting for theta. Theta is a variable that is equal to 0 in the void and equal to 1 in the material. Okay. We can rewrite the compliance using the dual complementary energy principle in terms of the Cauchy stress tensor and the homogenized tensor C star. And what is most important, we need to determine a constitutive law to express the stress tensor as a function of the displacement using the homogenized tensor. So in this framework, what we basically have done is determining a way to express this domain omega in terms of these two parameters, theta and C star. And so how does the homogenization method work? Well, it's an iterative scheme in which we need to determine what is called a composite optimal topology. So in this case here, we have a cantilever beam which is clamped to the left. We have a vertical load which is applied here to the right. We start with a homogeneous initial distribution of the material, and the composite homogenized structure is the results of the optimization step is this structure. So this is the results of the first step that I mentioned at the beginning of my talk. And in this structure, we can clearly identify the void, which is the white region, the solid material, which is the black region, but also an entire region of different levels of gray, which represent composite structure. They are neither void nor completely solid. Okay. So once we've determined this, of course, it is clear that this structure is not manufacturable because we need to provide an interpretation of what this intermediate density represent. And so the second step of the algorithm is to penalize the intermediate density, so the gray areas, by projecting this composite optimal shape on a set of real topology, which is what is sometimes called post-process structure, for example, via the dehomogenization procedure. And there have been several recent work to deal with this in the group of Grégoire Allaire and Olivier Pantz, and also by Alex Ferret and co-workers and many other authors. So in this context, both of the steps are clearly expensive because within we are computing the stress that we need to solve the linear elastic problem, and we need to compute the stress tensor in order to update theta and C star. Indeed, the solution that we see here, the homogenized solution, is obtained as a sequential laminate in which we have layers of void and material. And the orientation of this layer is determined upon the eigenvectors of the stress tensor. So this to say that we need to solve multiple times the linear elastic equation, and in both step 1 and step 2. But generally speaking, step 1 is the one where the most computational time is spent. Okay. So the first contribution that I want to present today is a way to try to improve this algorithm. This is a joint work with Antonio Huerta and Guillem Barroso, and the idea is to devise surrogate models to determine what we define as quasi-optimal topologies. So the idea is, in the framework of this algorithm that I showed you earlier, to first train a neural network to extract the most relevant features from a data set of optimized topologies, and then bypass this intermediate step by using this neural network, the trained neural network, to predict the composite quasi-optimal topology. So we end up having a topology which is something in between these and these, because of course the specific setup that we're going to study has not been seen by the neural network before. And so once we have this quasi-optimal topology, we can again perform the penalization of the intermediate density in order to retrieve a manufacturable structure. So how do we do this from the practical purpose? Well, we rely on a autoencoder architecture. So the idea of the classic autoencoder is to receive as input a certain vector of information. In this case is an optimal topology, which is described with element-wise constant values and is obtained by a homogenization process. Then we have an encoder part, which is used to compress the information towards a latent space, and the decoder part, which is used to reconstruct the optimal topology from the neural network model. And since here we have a constant value per element, basically we can treat our optimal topology as images, okay, and exploit all the knowledge about neural network techniques that come from the computer vision community. There's a drawback in all this, which is the fact that once we've trained the neural network, in order to assess, evaluate a new instance of the network, we do need an optimal topology as input. So this approach actually does not allow for design space exploration. To do so, we decided to enrich this autoencoder structure by introducing a parameterization of the problem under analysis in terms of the location where we apply the force and the orientation where we apply the force. And thus introducing this feed-forward network that links the information of these parameters that describe the problem with the latent space. But again, this still suffers from the computational drawback of needing an optimal topology as input. So we decided to get rid of this first encoding part and thus obtaining what we denote as a parametric autoencoder, which links a set of parameters that describe the configuration of the system to a latent space. And then there's via a feed-forward network. And then there's a decoding part, which allows us to retrieve the optimal topology. So let's see how this works. We took our favorite cantilever beam example. This is clamped to the left, and we allow the position of the force to move around this portion of the boundary with orientation that varies between 0 and 180 degrees. So we constructed a data set using 2700 optimized topology via homogenization, and each image has size 12,000. So it's the number of cells that we have in our domain. And here at the bottom left, you can see a visual representation of our data. The blue dots represent the training and the validation set, and the red dots represent the cases which are unseen, so the test cases. And specifically, what happens if we take a point over here in the green star, which is not seen by the original algorithm, and in a region in which we do not have information neither on any of the neighboring configuration. Well, the high-fidelity optimized topology looks like this, whereas the quasi-optimal topology that is provided by the neural net has this form. And clearly, this topology, that it's quasi-optimal topology, is not particularly good in the sense that it's not mechanically admissible. Here there are holes that appear, and so the performance of the expected compliance of these topologies are not particularly good. But already with eyeball norm, you can tell that the major feature of the two topologies are pretty similar. So using this to, instead of solving the entire high fidelity optimization loop, to provide a surrogate-based initialization to the algorithm, we can retrieve an optimal topology, which is indeed much more reasonable in terms of its mechanical configuration, and also the major features from the high fidelity solution to the left and the right surrogate-based optimization are actually well captured. If you look more quantitatively, to the compliance and the volume, we see that there's approximately an error of 10% with respect to the high fidelity solution. But again, this should not be particularly surprising because we are actually using a reduced model to solve the optimization problem. And it's well known that this model tends to provide suboptimal configuration. But what's really interesting about is observing the computational cost of this problem. The left configuration needed 10 iterations to get to a composite optimal structure and 51 with penalization. Whereas to the right, we only perform 1 iteration to get to a reasonable composite structure and 14 penalization iteration. Indeed, we could also improve these results because this first iteration is not really needed. We could perform some smoothing or some post-processing of the output of the neural network and further reduce the computational cost. So using surrogate-based models for quasi-optimal topologies indeed provide a significant advantage in the first block of the optimization loop that I mentioned at the beginning of my presentation. But looking a bit more closely to this result, but it's exactly the same also for the high fidelity topology, what we can see is that the quality of the topology is not necessarily good, because if you look at these boundaries, they are pretty jagged, pretty dashed. So the following topic that I want to present is a way of enhancing this topology optimization results by coupling them with anisotropic mesh adaptation. And this is a work that I've been doing with Daniela Raya during his master thesis. And to do so, we basically, first of all, change completely the paradigm of optimization. Instead of considering a homogenization method with a piecewise constant representation of the topology, we consider a phase field approximation. So we use a diffuse interface approximation with a phase field variable phi. Phi equal 1 represents the solid. Phi equals 0 represents the void, and the intermediate configuration of phi between 0 and 1 represent this transition, this diffuse interface. So we are getting rid of the abrupt variation that we had earlier by introducing a smooth variation with very localized gradients in this shaded area over here. So in this context, we can follow the same idea that I presented earlier for homogenization. We start from our compliance minimization problem, and we follow the idea in the seminal paper by Blaise Bourdin and Antonin Chambol to rewrite this problem in terms of a phase field variable. So we now express omega in terms of the phase field variable phi. And then we follow the idea in the work by Takesawa, Nishiwaki, and Kitamura to define the material properties using SIM. So let me go step by step. Now that we've defined our design variable to represent omega in terms of phi, clearly all the geometric configuration, for example, the restriction on the volume, can be rewritten in terms of phi. The linear elastic problem needs to be rewritten again in terms of the variable u phi that now depends upon the geometric configuration represented by the level set. What was proposed by the group of Nishiwaki in this JCP paper was to express the mechanical response of the material, so the relation between the stress tensor and the displacement, using the solid isotropic method with penalization by Benzo and Sigmund. So basically expressing this tensor C as a function of phi, but not any function of phi, using a power P of phi. And specifically, we considered, well, they considered P equal 3, which was a bit the standard proposed by Benzo and Sigmund in their original work, and was later also proved from the mathematical viewpoint to be rigorous by Amstutz, Ferré, and other authors. So This is a choice, of course. We could consider, for example, ramp instead of simp to express this relation. But what's important is that this simp approximation allows us to penalize the intermediate configuration, okay, in order to get towards either 0 or phi equals 0 or phi equal 1. So in this context now, what we can do is write, again, an iterative algorithm in which we will need to solve again the state equation, so the linear elasticity equation. But additionally, with respect to what we did in the context of homogenization, we will need to solve some extra problem, which are called the adjoint problem, to compute sensitivities. This sensitivity is actually a topological derivative. In the specific case that I'm going to present, for the example that I'm going to present, the problem is self-adjoint. But for example, if we consider non-self-adjoint operators or linear or nonlinear, also nonlinear problem like Navier-Stokes, we do need to solve extra equation to compute these sensitivities. Once we have these sensitivities, following a bit the idea of the gradient method, the standard gradient method, we can update the design variable using these derivatives. And this first block is basically equivalent to what I presented in the context of homogenization to get to a composite optimal solution. After that, we still need to penalize the intermediate densities. And if we want to achieve a good representation of the boundary, we will need to perform some mesh adaptation. So let me try to go a bit into the details of step 3, 4, and 5. So step 3 is the design update. So again, if we take our cantilever beam clamped to the left with a vertical load applied in this right portion, the iterative algorithm will determine a set of configuration. How does it do so? Well, first we need to define an augmented Lagrangian, calligraphical tilde. This augmented Lagrangian encapsulates the information of the objective functional, so the compliance, the state equation, so the linear elasticity equation, and also the, very importantly, the volume constraint. And so to move from one iteration from the initial homogeneous distribution to the following one, we need to solve a reaction diffusion equation to update the design variable. So the design variable, again, remember, is phi in this context, the phase field variable. We introduce a fictitious and artificial time to evolve the phase field. The driving force will be this sensitivity, which represents indeed the topological derivative and also the contribution of the volume constraint. So this is the reaction term. And the diffusion term is this Laplacian scale by this factor kappa, which is basically a regularization term. So by running this reaction diffusion equation, what we end up having is this configuration at the bottom right, which looks like an optimized cantilever beam, but it's kind of blurred. So the optimal design has these diffuse boundaries. So at this point, we need to penalize these intermediate configurations, and to do so, we introduce the notion of double well potential, again following the work by Nishiwaki and co-workers. And so we define a new potential calligraphic F, which is basically a combination of the sensitivities that we mentioned earlier and a double well functional, which has two minima, one associated with phi equals 0, so void, and one associated with phi equal 1, so material. And the intermediate configurations are then penalized. So to perform this algorithm here, this evolution to the right, what we need to solve is a modified reaction diffusion equation, in which we still have the fictitious time and the Laplacian as before, but we are now replacing the sensitivities that we introduced earlier by the derivative of this double well potential. And this allows us to achieve an optimal design configuration with sharp boundaries. But we are not happy yet, because if we look a bit closely, The one on the right is what we would like to get, but what we do get from the algorithm is this jagged representation, which clearly is influenced by the underlying mesh that has been used for computation. Of course, to get arbitrarily smooth boundaries, we could resort to using a very fine mesh. This is computationally very expensive, and so what we want to do is perform mesh adaptation. How so? Well, we basically noticed that the high resolution regions are associated with the transition between material and void, or material and material, material and fluid, depending on the problem that you want to study. And these transitions are associated with large variation of the phase field variable, so with large values of the gradient of the phase field variable. So the gradient of the phase field variable allows to determine the location of the mesh elements to be refined, but also the target size, shape, and orientation of these elements. And indeed, to do so, we construct an anisotropic mesh adaptation strategy following the work by Micheletti and Perotto, and later we've extended it also to the context of more sharp representation via level set in this paper. The idea is to devise a reconstruction of the gradient, okay, which is performed patchwise by performing a weighted average of the gradient of our finite element approximation of the phase field variable on the patch that comprises all the triangles that share either a vertex or a face with the triangle K. Okay. Once we've done it and we've constructed this reconstructed gradient, we can follow the idea by Zenkiewicz and Zhu to devise an indicator to perform locally mesh adaptation, so a recovery-based indicator. What is critical to perform in order to select not only the local mesh size, but also the shape and the orientation of this element is to determine an anisotropic version of this estimator. So basically rewriting this estimator in terms of lambda 1 and lambda 2, which represent the semi-axis of the ellipse that circumscribe the generic triangle K, and the eigenvectors R1 and R2, which are associated with the two directions of this semi-axis. So by controlling not only the mesh size H in the element K, but controlling specifically lambda 1, lambda 2, and R1 and R2, we are able to appropriately orient the element and stretch them as needed. So how does this work from the practical viewpoint? Let me show this example again of a cantilever beam. We start with a mesh of 14,000 triangles with an initial material distribution phi equal 0.5 and a target volume of 45%. So we perform phase field topology optimization using isotropic meshes or anisotropic meshes. With eyeball norm, you can see that we can get similar results between these two approaches. And quantitatively speaking, if you look at the value of the compliance and the error that we perform on the target volume, they're all of the same order and within a range of acceptability. In terms of number of iteration, they are almost comparable. In the case of the anisotropic meshes, we need to perform a slightly more iteration. But what is critical to observe is that the underlying meshes are way coarser in the case of anisotropic elements. So although we need to perform, in this case, 12 more iterations, each iteration is less expensive from the computational viewpoint. And if we zoom in the region where the elements are located, it is true that both approaches, both isotropic and anisotropic, are capable of localizing the elements in the appropriate region. But it's true that since not much is happening in this tangential direction to the interface, it's using anisotropic meshes allows us to reduce the number of elements that are located in this specific region. So we do know now how to construct quasi-optimal topologies and how to improve the quality of the meshes. But this we can do for a specific set of parameters. So for one configuration, for one run of the high fidelity optimizer. So the last topic that I want to present is trying to couple the two approaches by generating not only quasi-optimal, not quasi-optimal topologies, but quasi-optimal adapted meshes. So can we do mesh adaptation through neural networks? And this is the work of the master thesis of George Zamberlan. And the idea is, in the framework that I've just presented of phase field topology optimization, to train, in this context now, a graph neural network to extract the most relevant features from a data set of adaptive metrics that are obtained with the algorithm that I mentioned earlier. So we now preserve the first block of the algorithm. We are not touching it, but we are employing, instead of a mesh adaptation procedure, which might be expensive, a graph neural network to predict the mesh. So we still solve the reaction diffusion equation with the augmented Lagrangian. That part isn't touched, but now we modify the penalization term of the intermediate density in order to rely on these quasi-optimal meshes. How this graph neural network work? First of all, contrary to what I presented earlier, which was a feed-forward network and a decoder, here we're working with a graph neural network. So we can exploit the connectivity information related to the finite element mesh in this context. So the input is represented by a matrix of an anisotropically adapted mesh. We have a graph autoencoder in which we compress the information towards a latent graph, and there's a bunch of technicalities that I don't have time to enter in. We do graph augmentation, convolutional layer, top K pooling, and so on and so forth. And we reconstruct a metric as an output of the neural network. And again, we actually tested different configuration. What I want to present is a configuration in which we actually train 4 graph neural networks, one for the component M11 and M12 of the metric, one for the absolute value of the component M12, and another one for the sign of M12. M12 is responsible for the stretching of the elements. So it's very important that not only we capture the magnitude of the stretching, but also the direction in which we are stretching in order to retrieve good results. So with a data set of 16,000 adaptive meshes, we can now exploit the graph neural network architecture to work with fairly larger input data. So each graph size is of the order of 250,000, contrary to the 12,000 that we used for the graph for the feed-forward network at the beginning. And we are indeed capable, starting from a data set of meshes representing different configuration in which we move the force along this boundary and we change its orientation, to reconstruct a mesh which, qualitatively speaking, has comparable in terms of order of magnitude number of vertices and elements. Visually speaking, we are refining in the same region. And actually, if we zoom in, we are able also to identify the specific region. Some are perfectly retrieved, others are less, the approximation is less good, meaning these elements are slightly more isotropic than this one, which is what is responsible for this slight increase in mesh elements. But the question is, can we use this reconstructed mesh as a quasi-optimal mesh in our surrogate-based optimization? So on the left, we have the high-fidelity mesh adaptation, the optimizer with a high-fidelity mesh adaptation. And on the right, after constructing the diffuse interface optimized topology, we rely on the graph neural network to project this topology onto a space for penalization. And visually speaking, the results are comparable. If we look closely to the computational cost, the first two steps are unchanged. So they rely on the phase field optimization that I presented earlier. So we are not trying to optimize them. What we're trying to optimize is this second portion with the penalization. And for the high fidelity mesh adaptation, we require 38 iteration of penalization and adaptation, whereas with the surrogate-based mesh adaptation, we don't need any adaptation and penalization step. For this specific case, there are some cases in which we need 1, 3, 5 iteration in this last step. But what's important to stress is that it's always at least one order of magnitude smaller than the corresponding case of the high fidelity mesh adaptation. So I presented first a way to improve topology optimization by means of quasi-optimal topologies trained by neural network, a way of improving the boundary representation, and finally a way of improving the computational cost of this boundary representation by quasi-optimal meshes. So let me briefly wrap up everything. So the objective of this talk was to present how shape and topology optimization algorithms can benefit from the coupling of high fidelity and surrogate models. Clearly, the end goal would be to intrinsically couple them using a multi-fidelity setting. What's important to notice in these problems is that the quality of the underlying mesh is critical. So mesh adaptation, specifically anisotropic mesh adaptation, is crucial. But this step could be very expensive, especially in 3D. So resorting to neural networks to determine quasi-optimal topologies and quasi-optimal meshes offer competitive solution to improve the efficiency of this algorithm. And of course, the end goal would be to go back to the great challenges for use or related to sustainability and resiliency, and treat thermal fluid problem, thermal fluid porous media problems, so Navier-Stokes-Darcy, Navier-Stokes-Fourier settings, and accounting also for the information of reduced representation of the physical variables, so reduced representation of stresses, of velocities, temperature, and so on and so forth. And that's it for me. Thank you very much.
Thank you very much, Matteo, for this very inspiring lecture. We have some time, a couple of minutes before we move to the General Assembly of SEMNI. I'm seeing if there is any question in the chat in the YouTube channel. Apparently, this is not the case. But I would like to pose you a question about your graph neural networks.
Yeah.
Because they are quite popular at this moment, but also quite famous because of the difficulties of scaling the size of the mesh. They are computing intensive type of networks. So how do you plan to extend this technique to bigger meshes, particularly in 3D meshes? Do you find any difficulties in this sense?
Yeah, you're completely right. It is an issue, or it's a limitation of the method. We've only slightly seen it at the moment because we are working in 2D, but I completely agree with you that going to 3D will represent a major might represent a major bottleneck. I've seen some recent work in which there are approaches in which massively parallel architecture are exploited to perform basically training of sub portions of the graphs, but we've not looked into it yet.
Mm-hmm. Okay, thank you. Well, it seems that there is no other question in the chat. through our YouTube channel. I don't know if there is any other question, Marino. You
Well, I mean, I just want first to thank you, Matteo. I mean, I know how difficult it is to give these cold lectures on to a screen, and yours was very nice and interesting. And not being not having worked on this field, I have a very general question for you, and it's the following, right? So when we as humans have to solve a problem like a mathematical problem, so we combine our previous experience with our reasoning about the specific problem that we have in front of us, right? And it looks like you're asking the computer to do something that looks more and more like this, right? You're combining this previous experience with the analysis of the specific problem, and so my question is, how do you see this going, right? I mean, in terms of how we as humans will interface with these engineering analysis problems, right? We know ChatGPT, right, where you give like broad you pose broad problems using words, right? So how do you see this evolving in terms of being able to give a machine training about what is known about this kind of topology optimization problems in broader sense, about our eyeball norm, our visual inspection of the solution and so on, and doing this to solve at the end engineering problems. So I mean, sorry for the broad question, but
no, that's actually a very open question, in the sense that it's true that these machine learning techniques, but also more standard approaches like model reduction, projection-based methods can accelerate significantly the exploration of the design spaces. But at the end of the day, the engineer work is interpreting the results, and in that portion, I think is where a lot of work will be put. Well, there's already work being done in this context, but making these models capable of interpreting the end results, and in my opinion, that is the main challenge, because such interpretation needs to be based on, as you mentioned, on the specific exploration of the data, the observation of the results and the previous knowledge, and shouldn't be biased by irrelevant information, or information which is redundant, or possibly information which is wrong. Okay, so that is a big challenge, making artificial intelligence being able to identify those aspects, select them appropriately, disregard the not relevant one. I believe it will be a very active field in the upcoming years. Yeah.
Thank you.
Okay, once more, Matteo, thank you very much for this very interesting lecture, very inspiring. Thank you so much for accepting our invitation to be here today. And well, I think it's now time to close this session. We are all invited to join the SEMNI General Assembly, which will take part in a moment through Teams. So, well, thank you, Matteo. And
thank you. Thank you all.
See you soon. Thank you.
See you soon. Thank you. Bye-bye.
Bueno, muy bien, Mateo. Oye, muy chulo.